Welcome to the Cosmos Safari podcast, where the universe is closer than you think. I'm your host, Dave Farina, and with me again today is my fellow amateur astronomer and co-host of the podcast, Rob Webb. Hey, Rob.
Hey, how's it going?
Awesome. Thank you. And with us also today is Dr. Niel Brandt. Niel is the Verne M. Willaman Professor of Astronomy and Astrophysics and Professor of Physics at the Pennsylvania State University. Dr. Brandt is joining us today to speak specifically about his outreach through summer teacher workshops as well as his primary research interests. This summer's workshop, The Lives and Deaths of Stars, will be held on July 17th through 21st at the Pennsylvania State University. More information is linked in the description of this podcast. His primary research interests are the growth of supermassive black holes over cosmic time, black holes versus galaxy connections, deep cosmological multi-wavelength surveys, supermassive black hole winds and feedback into galaxies, sample-based studies of active galactic nuclei, extreme active galactic nuclei as tools, X-ray astronomy and high-energy astrophysics, and deep, wide, and fast cosmic surveys. Dr. Brandt, thank you so much for joining us today.
Pleasure to be here. Thank you for having me.
Now, before we go any further, if those are your primary research interests, what are your secondary research interests?
Oh, I have lots of other things. I mean,
I've got more fingers. We can keep going.
I do a lot of work on cosmic surveys, and one of the reasons I like working on them is they throw up lots of surprises unexpectedly. I've had people in my research group go off and just study galaxy evolution from an X-ray perspective, or I had someone who discovered new types of X-ray transients. And so those are other interests that I didn't choose, but that the universe kind of sent my way. And so I couldn't resist. So we chased those down too. Yep.
So I know you through these workshops. I don't know how many of them at this point that I've taken. I think there's at least 5 or 6. Do you know offhand how many different workshops you've done over the years in terms of different topics?
Oh, for me specifically, I've done, I think, 4 different topics over the years. I've been doing the workshops for about, probably just over 20 years now.
Wow.
And, this summer I'm actually making a new one that I haven't taught before. So this might be my fifth subject area.
Rob, I don't know if have you been to any of these workshops?
I have not been to any of them. I have been to Penn State for a couple different things, but not for the summer workshops, unfortunately. So I would love to go see one. Like this sounds really exciting just from what you sent me and what I've gotten through email and such. It looks awesome. Like I would love to be able to go and grab some stuff that I can use in my classroom. But yeah, so what actually got you into the astronomy field, and in particular, like what made you choose then stellar evolution, like the life and death of stars, for your workshop?
Oh, for the workshop. Okay, so that's a lot there. So, well, I've always been interested in space and astronomy ever since I was a little kid. I remember, back in elementary school, telling kids that I wanted to study space, and so that's always been an interest of mine. And, I went off, and for a while I was a physicist. I got excited by particle physics for a while. But then when I was in college, I started doing some summer research on astronomy, and I went back in that direction, and I've just been doing that ever since. So that's how I got there. And then in terms of, the workshops, well, I greatly enjoy teaching those. I grew up in a small rural town in Wisconsin, and, Pennsylvania has a lot of rural school districts. So I figure it's a way that I can, pass on, astronomy to other kids out there through their teachers, who might be excited about space in one way or another. And if their teachers know a good amount about galaxies and black holes and cosmology and stellar evolution, then they'll be able to teach their kids better. They can give their kids, materials that can let them learn. And that's kind of where I'm coming from.
What would you expect as a teacher to come up there, like in terms of, what's the commitment on their end?
Okay, well, so the workshops are fairly intensive for 1 week. So it's 1 week pretty much all out, with the workshops. And then in advance, we do ask the teachers to do some reading. It's a reasonable amount. We have them, read some material either to build up foundational knowledge so that the workshops can then expand upon that, or ask them to actually read some of the material that we'll then review during the workshops. And that process of experiencing something once, forming a lot of questions, and then having chance to ask lots of questions during the workshop can really solidify things.
I'm looking down at my wall of books behind us here, and it's funny because I really remember the black holes and time warps by Kip Thorne that you had us read before the black holes workshop. And I'll tell you, Neil, like every time I come back to, well, how do I know this? Because I have all these things that I tell my students now, and a lot of them are from the workshops. And I truly mean that. I cannot tell you how valuable that has been for me, especially early in my career. As I said, I've done, I think, 5 of them, specifically on astronomy, and I've done a few other workshops up at Penn State for a week with various other topics as well. And these workshops have really, provided me as a teacher a very strong foundation to know, even if it's things that I already kind of thought I knew, it was validation that my thought process was right, and I could bounce it off you guys because I had a whole week where we could, have those conversations. And I do tell people whenever we discuss, these workshops, and I'm trying to get people to go because I really would like to have more people experience what I experienced. I tell them one thing I like about you, Neil, is you never leave anybody in the room like not understanding before you move forward. You're very good about that. These topics are very challenging, but you always have a way. I remember like the sticky notes on the board.
Still do it.
You still do it. Yeah. It's just such a great technique. And as a teacher, you're excellent. I know research is your thing, and you're very good at that, but I can say from personal experience, your teaching skills are second to none.
Well, thank you. Appreciate that. Anyway, we certainly still have a strong emphasis on participant questions. I would say we spend 30% of the time, or sometimes even more, just answering questions from all the teachers who are attending the workshops.
Right.
And I think that's the right way to go, because if someone has a question, it's almost certain that some other people in the room have that question too, and that dialogue back and forth, even if it's sometimes a little chaotic and so on, nevertheless, I think is extremely valuable for clarifying concepts for people and making it so that when people leave, they feel, I really know this. I could go up in front of a classroom and teach this. That's what we're aiming to do. Let me say that not only do we, just give you a bunch of content material through lecture type format, but we also spend a lot of effort developing activities that teachers can learn about and can bring back to their classrooms. People who have helped run the workshops, or indeed have run their own workshops, such as Dr. Chris Palma, who's a outreach and education specialist here at Penn State, although now he's moved on to administration, unfortunately, and other people like Mr. Glenn Goldsboro, who is a Pennsylvania teacher, a very skilled Pennsylvania teacher, have done an excellent job bringing often already classroom tested activities to the workshop. And I think that must be extremely valuable. Hopefully you use some of those in your classroom.
I have I believe is the balloons and the foil experiment one. That one's from the workshop, and I just used that 2 weeks ago.
Great.
So yes, I am.
Well, here, how about this? Assume that I've never been to a workshop, which I haven't. Sell me, like, why should I go to Penn State, make the drive, get a hotel, whatever I need to do? Why should I do that when I can just sit on my phone and look at TikTok and find some astronomy stuff on there? Like, why can't I just go on YouTube or go on Google and find some stuff? Like, what makes the experience there better than trying to, try to take a sip of water through the fire hose that is
Right.
the internet.
Right. Well, again, so we spend a lot of work preparing an organized, week-long, in-depth workshop. And so the material is already designed to fit together in a logically consistent way. So rather than just getting like a one-off half-hour YouTube video, you get a much more substantial experience. You also, as has been mentioned, have the opportunity to ask lots and lots of questions. And sometimes, I think we probably all appreciate that not everything on the internet is absolutely true. And you have the opportunity to ask someone who hopefully through decades of experience now has a good critical assessment about what do we actually know and what do we not actually know.
Just to clarify, Rob had mentioned a hotel and some other things, and I know there is a level of stipend that comes along with this for those types of things.
Yeah, let me mention that briefly, and then I'll go back to the other things. So, yeah, there is. We have been very fortunate over the years to get some support for teachers. This is often used to help teachers who are coming from underserved districts across Pennsylvania, typically, but sometimes also across, from neighboring states, and that is used to provide stipends that can cover hotel, that can cover some travel expenses. This is not an enormous amount. It's about $1,000 per participant. And right now, last year, for example, I can say when we ran the workshop, we were able to give 12 of these stipends to people who otherwise just simply didn't have the funding from their district or anywhere else to be able to attend.
That's excellent.
Yes. So we do our best with that. And then, in addition, we have had a number of people come even when we couldn't give out stipends. I mean, I wish I could give stipends to everybody. It used to be possible to do that in the good old days. Now, unfortunately, education and public outreach funds coming directly from NASA, for example, are very tight. And it's just not possible to do that. So we do everything we can. In fact, the National Science Foundation funds some of those stipends. That's a very generous and important thing that they do. And the Department of Astronomy and Astrophysics here at Penn State has generously supported some of those stipends. And of course, the department has not only done that, they provide the classroom space, they provide administrative support to allow the workshops to happen. And so it's not like somehow I just do this by myself. I mean, the department helps, the National Science Foundation helps, NASA has helped over the years, and so on. So yeah, that's a few words about the funding, and then going back to finish this, your original question about why should I go. The final thing I would say, aside from this organized, structured content knowledge that's been put together to make sense in a consistent way, and the ability to answer questions, the final thing I would just say is, again, we do have all these activities that have been often classroom tested by a Pennsylvania teacher who's very skilled at these things. And that's an extremely valuable thing I think we bring to the table. I'm sure you can find these activities on the internet too, but being able to talk to someone who's actually done these in their classroom, who says, yeah, this part of it works, and for this part of it, it doesn't work, and for this part, it does work, but you have to do this approach, and then it works. You get that actual hands-on experience.
You get like a little beta testing with it,
yeah,
as you're at the workshop.
Yeah, you absolutely, you get a chance to beta test it yourself at the workshop.
You're the student,
and then,
right? You're the
and
student.
then and then in addition, you hear from a teacher who's actually done these things in the classroom, who knows how students react to these exact activities, and tells you, well, this part's going to work, and maybe you might want to skip this part if you're at this particular grade level, and so on. Yeah. So those are the things that we can bring to the table that I think you can't get off, YouTube or the internet generally. And all I can say, in terms of proving our value, is we are required to, and we take very seriously to have, at the end of the workshop, we have evaluations where the teachers anonymously are able to tell us how we did. And those reviews have generally been very positive. So it seems to work.
It
And
works.
so I'm happy with it.
I wouldn't have been back 5 times if it wouldn't have worked.
Right. Yeah,
They're
it seems,
excellent.
yeah, great. So it seems to work in that sense. Maybe someday the internet will be so good, that an artificial intelligence will be able just to replace me. But I don't think we're there yet. Yes.
I'd like to turn the conversation towards some of the questions that I have from
Sure.
some kids that I know.
Great.
And Rob, you'd like to start that off?
Yeah, sure. I guess one of the questions that my son asked was, do black holes move, and should I be scared of them?
Right. Okay. So yes, the answer is they do move. So if you could fly up and look at a black hole, first of all, it wouldn't be like a whirlpool out in space or something like that. It would look like a black sphere. That's what it would look like, and that black sphere is an object that can move. And in fact, that's from a theoretical perspective. And then from direct observations, we have, for example, discovered many stellar mass black holes in our own galaxy. These are often in binary star systems, and we can know the black hole is there from studying the details of the binary star system, and then we can measure over the years the motion of that binary star system, and unquestionably those systems are moving. And in fact, interestingly, they're often moving very fast, and that is likely because at least sometimes when the black hole is formed from the initial stellar collapse that made the black hole, the black hole and the binary system that it's in receives a so-called kick, a natal kick upon its birth, likely from neutrinos getting out from the proto-black hole in an asymmetric way that provides this system with this kick, and it can fly along at 100 kilometers a second or more. So certainly these things appear to move. And then should you be worried about it? Probably not. I can't guarantee anything, but probably not. I mean, if it was a problem, the Earth has been around for 4.6 billion years. If it was a problem, it would have gotten us already. So
Right.
it seems to be that these black holes are rare enough, and space is just so big that although there are many of these in our galaxy, probably millions of isolated free-floating black holes, as well as black holes in binary systems floating around in our galaxy, space is still big enough and empty enough that the chance of an encounter is very low.
Okay, good. That's exactly what I told him.
Yeah.
Pretty
Great.
much. Dave, you had another one?
Yeah, sure. This is from Ryan, and Ryan asks, in what ways is the James Webb Space Telescope
No relation.
helping you with your overall research?
Okay,
Or
right.
I can say, will it help you in any way?
Well, absolutely, it will. Yes. There's many things I could say there. I'll just talk about two of them. So one really big thing that we're trying to understand is the growth of black holes in the very earliest ages of the universe. Okay, the first billion years, say, of the universe. The universe right now we think is about 13.8 billion years old. And during that first billion years, exactly how black holes, in particular supermassive black holes, came to be during that time is still a challenge to understand. We observe in the first billion years of our universe's history there to be billion solar mass black holes out there. So how do you grow a billion solar mass black hole in less than a billion years? It can be done. It's not like somehow we have no idea how it can be done, but it's not easy by any means. And so understanding where those black holes came from, how they grew, is something that is of high importance, and that the James Webb Space Telescope is clarifying. It's doing that, for example, by now discovering large samples of high redshift galaxies in a very reliable and complete way. And give the James Webb Space Telescope a couple of more years to operate, we should have excellent samples of hundreds or thousands of well characterized high redshift galaxies with known reliable redshifts. And then I'd like to study, in an average sense at least, the X-ray emission, which is what I do. I work in X-ray astronomy. The X-ray emission coming from those galaxies, which tells us about the black hole growth in them. So that's one way the James Webb Space Telescope is helping a great deal, is it's giving us samples of galaxies that we can then study at other wavelengths to understand how the black holes grew. So that's one big thing. Another big question we're facing right now is, how have black holes affected galaxy formation and galaxy evolution? We have good suggestions that black holes have had an important role in shaping what galaxies are like. And we have, I'm involved as a co-investigator right now on a James Webb Space Telescope program, where we have a sample of galaxies. We have a sample of active galaxies with actively growing supermassive black holes in them, where we have, via a technique called reverberation mapping, have directly measured their masses. We know their masses. And now with the James Webb Space Telescope, we hope to measure the galaxies in which those supermassive black holes live much better than before, to understand connections between the black hole and the galaxy. So those are examples of things that we're working on. Those are just two things that I happen to be very excited about. And yeah, absolutely. James Webb Space Telescope is great. It certainly is, a delight to see this working so well after, enormous amounts of money and person power, effort, and so on, has been spent. It's wonderful to finally get that payoff. By no means was, in my opinion, I don't know. I think it had a pretty good chance of working when they launched it, but I don't know. The chance of failure could have been 30%. I don't know, but it's these things are touch and go in my assessment.
I was heartbroken to hear about the micrometeorite impact almost immediately. That was
Yes.
this. Is that playing any role in calibration and things like that in your work, or is that just taken care of by everybody else?
Yep. The instrument teams and the mission teams,
They handle all that.
handle the calibration of those types of issues on
Okay.
our behalf. It wouldn't be reasonable to expect every single astronomer to learn the full system at a level of detail where you could characterize that. So thankfully that they help with that. But yeah, absolutely, that was very worrying. And hopefully it will be okay in the long term. It seems like things have been okay more recently.
One of the benefits of having multiple mirrors.
For example, absolutely, yes.
Right.
Yeah.
I have a kind of follow-up question to that, and it has to do with something actually at the Black Holes workshop that we had discussed, which was the LIGO, or I guess it was the LIGO facility, but just gravitational waves in general. And some of the preliminary things that I've been seeing are that they can almost work like a first alert system to an event like a black hole merger, or an event that could then now alert with the rest of the electromagnetic spectrum telescopes the ability to detect them in almost a sequence. And I, from my understanding, we have now full understanding from very, very recent activity. And is that something that you see being a breakthrough in your field?
Well, okay. So LIGO unquestionably has been, a major breakthrough, both from a physics perspective and from an astronomy perspective. And so far we only have one really good example of an event where we detected it in gravitational waves, and then we're able to detect it also electromagnetically. That was the merger of two neutron stars.
So just to clarify, electromagnetically, you mean the full spectrum. So that would be starting with gamma rays. Those would be received next. Is that accurate? And then
yeah. Well, okay, exactly. The pattern, is complex, but yeah, sure. The one that I was speaking of, yeah, was detected as a gravitational wave source. Was also detected at almost the same time in gamma rays, as you said, and then was followed up at many other wavelengths very aggressively. And that was a wonderful success. We certainly hope to have more of those. And people are working very hard to find such things. And many of the other um, events, the ones that involve two black holes merging together to make another black hole, a bigger black hole, those so far, perhaps as expected, have not shown so much of an electromagnetic signature. People have looked very hard for electromagnetic light signatures, associated with those, and have not found them so far very much.
So,
Yeah.
so we're doing all this research, right? And we have LIGO, we've got James Webb now. We have that I forget what the name of it was that took the picture of the black hole, right?
Event Horizon Telescope, yes.
Yes, that's
Yes.
what it was.
Right.
So what do you think? How does that sort of research? How does us learning this stuff? How does that help the growth and development of human civilization? Like, how how does that information kind of help us as a population?
Well, okay, so um, in terms of you're talking about, okay, there's a number of things I could say. For one thing I will say is, of course, the technology that was built up to enable things like LIGO
Right.
and the Event Horizon Telescope and James Webb and so on has many valuable spin-off practical applications. Now then, when you ask, what does that astronomical information do? You know,
It's
to
a tough
be able to,
question that my students often will
yeah,
ask
that's
me,
fair
like,
enough. Well, I
whoa,
mean,
what are we doing this for?
yeah, sure,
Right.
right. Okay, so it's not gonna solve world hunger or anything like that. So and it's not going to help us defend the country, but it makes the country worth defending. It's like any great culture. It's like not any, but many great cultural achievements. I mean, what do the works of Shakespeare do to put food on the table? Well, not so much,
Mhm.
but they are unquestionably, a towering accomplishment, and so on. And astronomy is like that. It does have valuable technological spin-offs sometimes. It also, I mean, of course, I would say astronomy also has served very well over the years as kind of a gateway to science in general, where
Mhm.
many of the people who, for example, have come through our astronomy program, either as undergraduate students or as graduate students, have gone off to work for NASA or to work for technology companies or aerospace companies, and have contributed greatly. I mean, I will just say, I mean, I have one of my former students who is doing national defense work using the mathematical and scientific skills that she originally learned as an astronomer.
Mhm.
She still does a little bit of astronomy on the side, but she is one of the people that is actually defending our country with scientific skills. I mean, I can't say
Right.
exactly what she does, but it's very important.
We'd have to
And
cut
of
the
course, I
podcast at
will
that
also
point.
mention, of course, that you know that there are telescopes uh, that that are like qualitatively are like James Webb or are like the Roman telescope, but instead of looking up, they're looking down. We have
Hmm.
telescopes in orbit right now that constantly monitor the Earth, looking for the thermal signatures of nuclear missile launches, and that is something that is keeping us safe. And
Mhm.
um, people have to be developed to make that kind of technology. And a lot of people get inspired by astronomy. They learn a great deal about using telescopes to look upward to study the universe. And then later on in their career, they come to appreciate that these things can be pointed downward as well and have very real practical utility.
Right.
And may someday, prevent a major American city from being destroyed by North Korea, for
Right.
example.
Yeah, I would agree. I think people see the headlines and they they just sort of get the first little bit of information. And I think in general, science communication could do better at showing those extra, this affects this, the
Right.
spin-offs. And I think the first thing when there's a discovery, it's, oh, that's funny. And then it's, oh, well, how can I make this do something different for us? Like, how
Right.
can I use this new knowledge to help us. And I think sometimes that gets lost in the communication out there.
Right. Yep.
But yeah, Dave, did you have another one?
I just would like to bring it back a little bit more to the stellar evolution topics, since that
Sure.
is the workshop.
Sure.
And in the news recently, we had the triggering of a positive energy coming out of a controlled fusion reaction in a lab. What thoughts do you have about that? I'm sure that it's exciting. I'm excited about it. I know a little bit, but I'd like to know your perspective on it.
Yeah. Well, yeah. That certainly was an excellent achievement. I would say that we are still far from having fusion reactions that practically provide large amounts of power to the citizenry.
I stayed on beyond just the news part of it. That was most people would have watched the actual science, briefing, and they mentioned that although it's net positive from the energy that that energy the laser puts into it,
Right.
the laser itself is so inefficient. It's like 300 times
That's
more
right.
energy goes into the laser than comes back out of the laser.
right.
So the laser itself is not, net positive.
That is correct. Fusion. Yeah. These fusion experiments are extremely challenging. I hope someday they will work out. I have seen, them always being, we're just 20 years away, and it's been
Right.
that way ever since I was an undergraduate 30 years ago. So, it's a very challenging problem. I can't rule out that there will be a breakthrough that will enable this to be productive. We're not there yet, but we're making progress.
It's like 3 orders of magnitude away, but that's actually not that hard if you look at history, I guess. We've
You can
made
look at
major strides
Yeah,
in
you can
that.
look at how many orders of magnitude we've already eroded,
Right.
and
Mhm.
so I certainly hope it will work in the long term. I cannot guarantee it, but I think it's plausible.
Mhm.
Yeah.
So for some of the people in the audience who are not as adept at this as we are, so the fusion is when hydrogen, typically molecules, smash into each other and turn into something different. I'll let you explain that. How similar, because we know fusion is what powers our sun, right?
Correct.
Fusion
Yep.
is what gets us the energy. Fusion is our life sustainer here from
Mhm.
the sun. How similar or different is the fusion that's going on in the sun in its main sequence part of its life? How similar is that to the fusion that was done in the lab? My quick understanding is that it's really not that similar, or at least it's only a part of that step.
Yeah. So the fusion that goes on in the sun, as you said, involves two hydrogen atoms merging together to form a helium atom. And that's what is ultimately providing the bulk of the energy that comes out of the sun. That happens naturally for the sun because of the enormous temperature at the core of the sun, and because of the fact that the sun is under enormous pressure, so the densities are very high in the center. So you're in a regime of temperature and density that is not straightforwardly achieved here on the Earth. So on the Earth, so far, we have had to take other approaches. And as Dave mentioned, the recent results have involved shooting very high power lasers into a small concentrated amount of material, and thereby triggering fusion reactions. So this is something that is not natural the way that it is for the sun. This is a highly engineered uh, circumstance, very much in contrast to what happens in the core of the sun. So yeah, it's very different, but the basic idea of taking, you know, um, lower atomic number elements and merging them together to make high atomic number elements, that basic idea still holds. And they hope to tap the enormous energy that is potentially available there ultimately to make fusion power. But again, honestly, I think we're a good ways away still. It's good when they have these breakthroughs, but this is a step along what's going to be a long path to practical large scale power. So hopefully that's addressing your question at some level. It becomes addressing it further becomes very technical, but that's the idea. Yeah.
Right. Yeah. I think I remember hearing it actually turns the hydrogen 1 into hydrogen 2. Is that really what's going on in the?
I'd have to go back and check. I don't want to comment specifically without having all my facts straight. Yeah.
Fair enough.
Do you see that, these experiments are going to be able to prove out any of our theoretical formulas that we've been using historically, even if it's not a net positive energy producer, or is that something that's already been done in the past?
Well, we think we have the underlying physics of fusion pretty well understood. We now understand quantum mechanics very well. We have managed to actually probe the core of the sun with many now ingenious experiments by measuring, for example, the sun's oscillations at its surface. That actually tells you things about what are going on deep down inside the sun. Or alternatively, we now have very good measurements of neutrinos coming from the core of the sun. And those tell you about the nuclear reactions that are making the sun go. I don't think there's a lot of uncertainty in terms of, the details of how the sun's fusion reactions work. We think we understand the conditions there very well. And we think we understand the underlying quantum mechanics very well. And then we have direct measurements from the neutrinos, for example. I don't think that these fusion experiments, I don't think their value is in helping us understand how the sun works better because we don't understand it very well. I think we understand the sun pretty darn well right now. Yeah.
Okay.
So I asked my son and his best buddy Owen. They were on our little FaceTime thing a little bit ago, and I asked them, hey, I'm talking to somebody who knows about how stars are born and live and die. What do you want to know? And they had two questions. Number one was, how do stars turn into supernovae? I think they said supernovas, but we'll let them go. And then also, do you think we'll see one in our lifetime? And I was impressed. My son's buddy Owen was like, well, I think Betelgeuse might be, but it sounds like that might be like 500,000 years in the future or something like that. So, so I guess my question is, how do stars turn into supernovae? And do you think we'll see one from here on Earth in our lifetime without using a telescope?
I think that's you want a naked eye supernova. Yes. You want a naked eye supernova. Yeah. Okay. I'll start with the first one. So supernovae, the classic type of supernovae, there actually is more than one type, but the classic type of supernovae arises when a massive star comes to the end of its life and it starts building up a large ball of iron in its core. And iron is a very special element in that you cannot productively fusion burn iron to produce more energy like you can with hydrogen and helium and carbon and oxygen and neon and silicon and sulfur. You can run all the way up to iron, but at irons, you can no longer extract energy by fusion burning iron. So stars build up this big ball of iron in their core, and ultimately this big ball of iron becomes unstable to gravitational collapse. It gets so massive it can't hold itself up, and it collapses, and it very rapidly, within a second or so, shrinks itself down from being of order the size of the Earth to being of order the size of Lancaster. I guess that's where you are. It shrinks down to be of order the size of Lancaster. So
that I got to comment. That is really fast. I mean,
yes,
when we talk about astronomy, we're talking about stuff in the hundreds of thousands to millions of years, and you're talking about a process that takes 1 second.
Like a second, yeah.
I mean, I'm trying to think about that in terms of compared to the speed of light. Like, what are we talking here? in terms of collapse rate?
Okay. So it's collapsing. I mean, not at the speed of light, but rapidly. I mean, here's the way you can kind of size that up. Remember, so the speed of light can go around the Earth 7 times. Light can go around the Earth 7 times in a second, something like that, right? And here again, you're talking about something collapsing from about the size of the Earth
Okay.
down to the size of Lancaster, say. So it's moving at a good fraction of the speed of light, 10%
Like a
the
tenth.
speed of light,
Yeah.
something like that. But it's not crazy. It's not 99% the speed of light or anything.
I don't know. I think 10% of the speed of light is pretty
It's
crazy.
pretty crazy.
It's fast. It's pretty
Especially if
fast.
that's the acceleration rate. Like that's not just the speed, that's the acceleration too, and everything. That's a lot of inertia to be moving fast.
Right. These are extraordinary events. And anyway, so then that collapse down to this small size liberates a tremendous amount of energy for for that short period of time while the star is collapsing. It is producing as much energy as all the stars in the rest of the universe put together.
Oh wow.
The universe? Not just the galaxy, but the universe?
The universe put together. All the stars in the rest of the universe put together is liberated during that fraction of a second.
In a stellar mass black hole, like this, or I'm sorry, in just a supernova, I mean.
Yeah, we're talking about supernova.
Wow.
I'm talking about one that makes a neutron star. I mean, not necessarily one that makes a black hole. Yeah, they produce fun. I mean, it's just extraordinary how much energy comes out. It's about 10. It's about 10 to the 53 ergs, and so that's that's a 1 with 53 zeros.
I gotta ask, what is an erg? What is an erg?
Yeah,
I have to ask.
Well, it doesn't matter if there's 10 to the 53 of them. I mean, again, that's a 1 with 53 zeros after it, so it hardly matters. It's a tremendous amount of energy. So
one of my geology professors, when we talked about the amount of pressure in the Earth, we made up our own units, and hers was sumo wrestlers in stilettos. Was the unit of pressure we were using. So
I see.
ergs, I don't know. Sounds funny.
Okay, sorry. Well, anyway, it's a standard unit of energy. In any case, yeah. So that's what a supernova is. It's a classic supernova is the collapse of a star's core, a massive star's core, down to form a neutron star, or in some cases, probably a black hole. Now, there is another type of supernova, but we'll leave that aside for today. We'll just focus on that one. I'll go to your second question then. Will we see one? Well, I certainly hope so. And I think it's plausible, but by no means guaranteed. I mean, you can look back historically, and we had a run when you were getting a good number of these things. You can look back for Kepler's supernovae. And I think there was Tycho Brahe had a supernovae, and Kepler had a supernovae, and those happened in a short span of time. So, people, when they estimate the supernova rate for a galaxy like ours, they speak of, a ballpark 1 per every 100 years, something like that. So I think it's quite plausible we would have one, but it's not guaranteed. We almost had one in our own galaxy. I mean, in some sense, we did back in 1987. In 1987, there was a little dwarf galaxy of ours called the Large Magellanic Cloud, where a supernova occurred. And if you actually appreciate what a galaxy truly is, I mean, the stars and so on that we think of as a galaxy is not really the main part of a galaxy. Galaxies, honestly, are giant configurations of dark matter that happen to drag a little bit of normal matter in along for the ride. The stuff that makes the stars and the planets and the people, that's just the icing on the cake. And so, the Large Magellanic Cloud, is orbiting within our galaxy's dark matter halo. It practically is a part of our galaxy, even if it is distinguishable. It's very nearby, 50 kiloparsecs or so away. And so, yeah, I think it's quite plausible we'll have one. If I could have one thing before I die, that'd be a good one. I mean, astronomically.
Agreed.
Yes.
Yeah,
Agreed.
to see one of those, that would be a wonderful thing. And I will tell you, I mean, astronomers take that possibility very seriously. People who right now operate neutrino observatories have codes running all the time, because as I mentioned, a lot of the energy comes out as neutrinos. In fact, 99% of the energy from a neutrino from a supernova comes out as neutrinos. They are constantly have codes running, analyzing the incoming neutrino data stream for the next supernova event. And they write proposals all the time to the major observatories. Every year they send them in and say, if we get a supernova this year, we want to take over control of the Chandra X-ray Observatory and observe the supernova, or we want to take control of the Hubble Space Telescope and whatever, and observe the supernova as much as possible. So I can tell you that astronomers take this very seriously. I mean, they spend a substantial amount of time and effort to monitor the incoming neutrino data and to write all these proposals for all the facilities. I mean, they take it very seriously. And the fact that they take it very seriously, and these are the experts, make me think that, yeah, it's quite plausible we would have one. It's also plausible we won't. I mean, it's just a numbers game.
It's a roll of the dice. Yeah.
If the rate was once a year, we could be very confident we'd have one. But with once every 100 years, well, that can fluctuate statistically. You might have a 300-year gap once in a while, or a 500-year gap once in a while. That's not outside the range of reasonable probability. On the other hand, if we're lucky, you could have 3 in 100 years.
What could be learned if we had something like this? I mean, what are the questions you would have if this were to happen?
Yeah, well, okay. So the next time we have one, it's going to be an enormous, bonanza for astronomy. One of the things that I think is most exciting, again, as I just said, most of the power actually comes out as neutrinos. All the light and so on. That's all beautiful pyrotechnics, but it's 1% of the power. So what will be extremely exciting is measuring large numbers of neutrinos that come out from the core of the collapsing star. We know these neutrinos will be there because from the supernova that happened back in 1987, we detected a small number of neutrinos of order 20 in total from 2 different neutrino detectors. One of them was in one of them was in Cleveland, Ohio. One of them was in Japan, and they detected of order 20 supernovae. If you look at how much neutrino detectors have improved since 1987, it's been enormous. The next time we have one of these events, we will likely have thousands of neutrinos detected. Each one of those neutrinos being time tagged to very high accuracy and precision. And so we'll be able essentially to watch the star collapsing in real time. You'll actually, by studying the detailed profile of the neutrinos coming out, you will learn exactly how stellar collapse proceeds, with high precision quantitative measurements, something that we just couldn't do with the 20 neutrinos we had back from 1987.
Right.
And you'll have energy measurements for all those neutrinos. And so, I mean, that's one that'll be a really fundamental thing, high precision measurements of stellar collapse. And that will immediately let all the people who write these computer codes, trying to work out the details of stellar collapse, this will immediately clarify which of those codes, which of those approaches is the right one, and what physical phenomena are occurring and which ones are not occurring. This as you probably would appreciate, is a very complex thing. The collapse of a star's core in 1 second is a complex thing. Knowing exactly what all the relevant physical processes are is not always so clear. And having real hard data that tell you this is the way to go and all those other ways are not the way to go, that will be incredibly clarifying.
So, we have a few minutes. I just want to discuss, we'll come back to the black holes again. One of the things that I remember from the black holes workshop that was repeated time and time again was that black holes have no hair.
Correct.
And I'd like just to clarify what that means, and how you just said that this stellar collapse was one of the most complex things, but yet black holes are actually deceivingly simple.
Yeah, that's right. Yeah, so this idea, black holes have no hair, what they're referring to there is, hair is there taken to represent complexity. If you wanted to describe mathematically the hair on your head, you would need millions and millions and millions of numbers to even start doing it. You'd have to describe each piece of hair, how long it is, what its curvature is, what its composition is, all that stuff. It takes huge complexity a huge amount of information to describe the hair on your head quantitatively. On the other hand, black holes, at least from our classical understanding of them, that is leaving aside quantum mechanics, which adds a whole bunch of additional wrinkles. But just classically, black holes can be explained by three numbers. One is the black hole's mass, one is the black hole's spin, and the third is the black hole's charge. Astrophysically, charge probably doesn't matter very much, for the same reason that we don't find large concentrations of charge here on the Earth. There's two different types of charges, and they tend to neutralize each other. So really, it's probably only mass and spin practically. And so, the understanding we have from general relativity is that black holes, in fact, are very simple objects. That they almost are as simple as elementary particles, which themselves can be explained by just a few simple numbers. And so if I understand, Dave, your question is, how do you get from something that has the complexity of stellar collapse down to something that's so simple like a black hole? And the answer there is essentially all the complexity is thought to be radiated away. And there's a famous theorem called Price's theorem that describes that. Essentially, Price's theorem says that anything that can be radiated from a black hole will be radiated. And so you can imagine, for example, a black hole that has a complex shape. Let's say the stellar collapse proceeds slightly asymmetrically and leaves an object, a non-spherically shaped object. That complexity can be radiated away to leave behind a spherical black hole. In particular, gravitational waves will be produced that radiate away that complexity. You could also imagine a black hole that starts off having a magnetic field. And we know stars have magnetic fields, and so it wouldn't be surprising if during the stellar collapse some amount of magnetic fields are preserved. But as soon as the black hole's event horizon goes up, there is no longer any ability to retain that magnetic field. You probably know the classic idea that no information can get out of a black hole, out of a black hole's event horizon. So the black hole's event horizon is worthless as an anchor for that magnetic field. The magnetic field can slip off the black hole and be radiated away. In this case, it's radiated away as light or electromagnetic radiation. So that is Price's theorem at work. So essentially, how do black holes get so simple from such a complex initial start? They radiate away all the complexity. That's
awesome.
that's the best answer I can give you. And again, if people are interested in learning more about that, there are nice descriptions of that, including in the Kip Thorne book that you mentioned earlier, that you say you have on your bookshelf back there. That explains it very nicely. I don't remember the exact chapter, but it's in there.
And I think I think that other book that I see down there, Rob, can you grab that one? The Black Holes and Time Warps one, and I believe Neutrino Hunters may have been the one that I did with the astroparticle physics folks.
Yep. Mm-hmm.
So yeah, that's the one. Here.
There you go. That's right. The answer is in that book. Yeah, the answer is in that book. If you want to know.
And I think that's another one that I had gotten from one of the workshops up there from a different group.
Yep.
So, I guess one of my other questions is, you've done a lot of research on black holes. Right?
Yes.
Based on your primary research interests that we read off. I'm curious as to what is something that you really want to know, but you just can't figure out right now. Like, what is that one thing that you're like, man, if I could just figure that out before I retire, that I'm done, like that sort of thing.
Right. Okay. Well, I can say a bunch of things. I'll tell you my personal thing of the past several years. We observe supermassive black holes growing over the history of the universe in large numbers. And we believe that these black holes affect their galaxies. But exactly what properties of a black hole, what properties of a galaxy promote the growth of its central supermassive black hole is something that is very hard to know. We observe many effects empirically. Black holes that are more, galaxies that are more massive are much more effective at growing their black holes. Galaxies that have large rates of star formation tend to grow their black holes better. Galaxies that are more compact have a greater concentration toward their center tend to grow their black holes better. But those are just a few of the possible answers. We also suspect that cosmic environment, whether a galaxy is in a cluster or in a very empty region of space, maybe that drives black hole growth. So one thing I really would like to know was what truly matters for supermassive black hole growth in galaxies.
Now,
if I could know the
I was just gonna ask, like, what makes that so difficult to research? Because it sounds like you have a clue, like you have an idea, and I feel like there's plenty of galaxies for us to observe. Like, why is that hard to figure out?
Well, okay, so we're getting there. We're getting there. We have, as I mentioned, we have identified all these correlations with galaxy mass, with star formation rate, compactness, and so on. And we have actually pitted those different drivers against each other using a mathematical technique called partial correlation analysis to try to ferret out which of them is truly fundamental. And we have some suggestions there, but the samples do not allow us to fully answer those types of things yet. With future observations, for example, by the James Webb Space Telescope, by the Roman Space Telescope, we hope to have enormous samples that will let us answer those types of things. So that's part of it. Another part of it is some of the drivers may be things that just simply aren't easily observable. I hope that's not the case. But, just because something has an answer out there doesn't mean that it has to reveal itself to us based upon our current technological ability to measure things. When we measure these distant galaxies, we can only measure the most basic properties of them. And sometimes even the most basic properties are measured in an uncertain way. And so sorting all that out is a real challenge. So that's something I really would like to know. Essentially, what matters for black hole growth in a galaxy? What is it that matters? That's something I would like to know. I would also like to know, as I mentioned earlier, where the first supermassive black holes in the universe came from. It's not easy to grow them. The simplest possibility is you just form a black hole from the collapse of a massive star, like we talked about earlier, and we just let that black hole feed and grow for a billion years or so, and it can grow to an enormous mass if it can be fed all the time, but that's not an easy thing. So some people have proposed that black holes may get a jump start, that large gas clouds that perhaps weigh 100,000 times the mass of our sun may collapse down in the early universe to form hundreds of thousands solar mass black holes. And that would be the starting point. And that gives you kind of a jump start in black hole formation, because instead of having to grow from 10 times the mass of the sun up to a billion, you only have to start at 10 to the 5 or 100,000 and have to grow to a billion. So it gives you a jump start. So I'd like to know, if I had to phrase it in a very pithy way, do the supermassive black holes get a jump start in their formation, or do they grow in the simplest way possible? That's something I'd like to know.
That's cool.
It's kind of like, let's to kind of try to tie this all together as we conclude today.
Sure.
Thought I had as you're speaking is, early universe, lots of gas. You were saying collapsing down. Are we talking about massive stars above and beyond the sizes that we're seeing in times today? Thousands, tens of thousands of solar masses as a star that has a very, very short lifespan as a result? Or are we just talking directly collapsing to a black hole? How would that
collapse to a black hole? It's that one. These would be direct. If this happens at all, and there's no guarantee that it does, but if this happens at all, it's thought to be direct collapse to a black hole. You don't form 100,000 solar mass star, which then collapses to make a black hole. It just goes straight to a black hole. Boom, one shot.
Wow.
That's a possibility.
In the cosmic microwave background radiation, we've had that for many decades now. We know the earliest stages of the universe. The Hubble got us back to, what was it, 300,000 or so years after the Big Bang?
Oh, no. That the microwave background was emitted 300,000 years after.
Oh, okay.
Hubble got us back to like 500 million years, somewhat earlier than that.
And then we're filling the gap in. That's what we're doing right now. We're filling the gap in between those two data sets that we have fairly well understood. And James Webb is the one that's doing most of that currently. You mentioned the Roman telescope. Is that going to be doing similar work, or is that going to be just something completely different?
The Roman will be doing some of that. The Roman telescope will be unique in that it will work in the infrared to a large extent, like James Webb, but it will have a vastly larger field of view.
Okay.
So instead of, James Webb gives you these little tiny pencil beam pictures of the universe in the places where you choose to point it very carefully and specifically. With the Roman telescope, they hope to observe a substantial fraction of the entire night sky with excellent sensitivity and with, Hubble Space Telescope type resolution.
Wow.
Okay. And so it will give us, as I mentioned, a truly enormous samples of galaxies that we can then study in great detail. So it will give us a broader picture of what's out there in the universe that you can't get so well just from these individual pencil beam observations.
All right. Well, thank you so much, Niel. I do appreciate your time tonight. Rob, I think you need to go to these workshops, man.
Yeah.
I don't think you have a choice now. You know about them.
Sounds fair.
And Niel, you heard it right there.
Okay.
You should expect Rob in your classroom anytime soon.
Yeah.
Okay. Great.
So yeah, we really appreciate it. We'd love to have you back sometime.
Okay.
There's so many questions that we could ask.
I think we asked maybe 10% of what we were thinking.
Yep.
So
love to have you back sometime. And thank you so much again. And keep looking up, everybody. Thanks for joining us for the Cosmos Safari podcast. I do want to mention we are trying to get this podcast off the ground. We've got a Patreon. We'd really like it if you guys could head over to our Patreon. I did put in some questions for Niel tonight in the Patreon. So that's one of the things that you'd be benefiting from by joining and being a member. That also is what's going to help us to keep the podcast alive and on the air. It's not free for us to do. So we really appreciate it if you are listening to head over to Patreon and help contribute Cosmos Safari, $3 a month or something, just to give us the chance to have great opportunities like we had tonight with Niel. So thank you, everybody. And
thank you.
Thank you. Thank you for having me.
No problem.
Of course.